Hello, so my name is Carolissen, and today me and my teammate Max Morris will be explaining to you guys about a two-phase simplex algorithm. Okay, so today we'll be explaining to you why we need to use a two-phase algorithm. We'll also be explaining to you what happens in phase one, why we need two phases in the first place as well, and we'll be explaining to you why we need a second phase and what we do in the second phase. We'll also be using an example to show you why we need and how it works and all of that as well. Okay. So first, why do we need a two-phase simplex algorithm? So we need a two-phase simplex algorithm to find the optimal or feasible area. Okay, so we can, how can I explain this? So when you see there's a greater than and equal to sign in one of your constraints, then you know you need to use the two-phase algorithm because you're not in the feasible area, and since we're not in the feasible area, we first need to go to the feasible area. So that's why you need a two-phase simplex algorithm to do that. Okay, so the slide just says what I said already. We use a two-phase simplex algorithm when we have a greater than or equal to constraints or sign. This then helps us to find the feasible area of our linear program or LP, and then we can find an optimal solution for the linear program. Okay. So now I'll be explaining to you how phase one works. So this will be our example for this, how we will be explaining to you with this example. This is how it will look. So we first have our objective function, which we're trying to maximize something. Let's say we're trying to maximize some profits. So our objective function is 3x1 plus 2x2, which is then subjected to two constraints. Our first constraint is x1 plus x2 is less than and equal to 4, and our second constraint is 2x1 plus 3x2 is greater than and equal to 9. Then our x1 and x2 must be greater than and equal to 0, which just means we don't have any unrestricted variables in our LP. Okay, so first thing you should do when you have a two-phase algorithm is to add your slack if you have a less than and equal to sign for any of your constraints, and then subtract your excess to any greater than and equal to signs as well in any of your constraints that has a greater than or equal to sign. Then also add your artificial variable. Okay, so artificial variable is just there so that we can subtract our excess and so that we can use a two-phase algorithm and to find the feasible area. Okay, so this is how the constraints would transform or change. So our first constraint where we just add slack because it's a less than and equal to sign, x1 plus x2 plus s1 of slack is equal to 4. Then the second one, 2x1 plus 3x2 plus our artificial variable minus our excess is equal to 9. Okay, so now that we transformed our constraints, we need a W row, okay, or a W function. So our W function is basically the sum of all our artificial variables. So how you would get that? You would make everything equal to this artificial variable. So this will change to 9 minus 2x1 minus 3x2 plus our excess, and then you would add that to any other artificial variables that you may have in your LP. We are lucky today, we only have one, so easy sailing. Then it will be W is equal to 9 minus 2x1 minus 3x2 plus our x's. Okay, then you're not done. You take it back over. You take everything back over except your constant value, which is 9 in this case. Okay, so then this will be our first table. Okay, so you can see 2, 3, minus 9 and minus 1, and then our right hand side is 9. And then the rest is just our normal primal simplex, where you take your objective functions values to the other side, make them negative or the opposite, which is minus 3 and minus 2. This is just you added slack, and then that's your artificial variable and your x's that you also added as well. Okay, so first we need to pivot, so we need to find our pivot column. How we would do that, we find the biggest positive value because you're trying to minimize the W row. So you try to find the biggest value that is positive in this row over here, which will be 3 in this case. So this will be your pivot column over here. Then we do a ratio test, which is the right hand side value divided by the pivot column, the value over here, which is 1. So it's 4 divided by 1, and 9 divided by 3. You don't use your z value or your w value for the ratio test. Okay, so you then pick the smallest value of the two, or however many ratio tests you have to do. We pick the smallest one. In this case, it's our second constraint row that we will be using as our pivot row, and then this is our pivot value over here where they intersect. Okay, this table over here. So this is that we got this by saying, okay, let's go back. Okay, so we got that next table by saying this value minus this value times it with the value or the row that to be pivoting over here, but in the next column. So this one over here. Since there's no variables, if you do this in Excel, you will say there's no value to use there. But afterwards, you say, then you say this value divided by itself, and then you copy it down to the other ones as well, and then you will get some values in your whole table as well. Okay, so you keep doing that until you have no positive values in your W row. So you can see we don't have any anymore, which is lucky for us. We don't have to do any more pivoting or anything like that. So now move on to phase 2, which my teammate will explain to you guys. Okay, thank you.
Hello everyone, today we're going to be discussing the phase 2 of this two-phase simplex method. This method is particularly useful when we don't have an obvious initial feasible solution for our problem. So in phase 1 we introduced artificial variables to help us find a feasible starting point. So now in phase 2 we'll remove those artificial variables and focus on optimizing our original objective function. So here's what the key values mean. We have the RHS, which is the right hand side. These values in the column represent the current solution. So for example, x1 is equal to 3x equals 1, and x2 is equal to 1x2 equals 1. So then we have the objective row, which is z. The value 11 is the current z-score calculated as 3, and then in those x values you put 3 and 1, and then that will equal to 11. And then we have the coefficients in the z row. These indicate how much each variable contributes to the objective. So for example, the 5 under S1 means increasing S1, which is like a slack, which would improve Z by 5 per unit. So in conclusion, the two-phase simplex algorithm shows us to find the feasible area when we cannot use a regular simplex. So we make use of artificial variables to solve phase 1, then solve the real problem in phase 2. By breaking down the problem into two phases, we ensure accuracy and reach the best outcome. Thank you so much for watching.